Good mid-morning to everyone. Thanks for everyone for coming. Today in this session, we're talking about uncertainty quantifications and Gaussian processes. And up first, we have Carlo Graziani from Argonne National Laboratory. He has a Ph.D. in physics from the University of Chicago. He's held roles at NASA Goddard, Enrico Fermi Institute in the University of Chicago, where he contributed to High-Energy Transient Explorer project and served as a research associate professor before joining Argonne in 2017 to focus on UQ and machine learning. So with that introduction, I'll turn it over to Dr. Graziani.
Well, thank you and good morning. As you heard, in my misspent youth, I was an astrophysicist. I refer to myself now as a recovering astrophysicist. Can we get the Zoom thing off the screen? Oh. Okay. Yeah, I could have done that too.
Click the X.
Yeah. Yes, I am technically trained, at least that far. Okay, so I work now mostly on machine learning and uncertainty quantification. I do a lot of work on the subject called Gaussian process modeling. Okay, so I think probably a lot of you are familiar with what a Gaussian process is, but I'll just give a quick informal introduction just to set the table for the talk. So a Gaussian process, it's part of a broad family of non-parametric methods. I guess you could refer to this family as kernel methods. They embed the ideas from optimal recovery, radial basis function, interpolation in a statistical context that allows one to reason quantitatively about model error. Informally, I mean, there's a formal definition of what a Gaussian process is. It's a type of stochastic process. Informally, I find it useful to describe it as an infinite dimensional multivariate normal distribution over a space of functions. So if you imagine like a Fourier series, and you think of the complex exponentials as the basis vectors of a vector space, then the Fourier coefficients are like the coefficients of a vector. And now you could imagine placing a multivariate normal in that infinite dimensional space that becomes a distribution over a space of functions. And multivariate normal is, of course, completely characterized by a mean vector and by a positive definite covariance matrix. The Gaussian process is analogously characterized by a mean function and by a symmetric positive definite covariance kernel. Now, the choice of the kernel is very interesting and impactful and consequential in Gaussian process modeling because it is, in effect, a choice of the character of the space of functions that you sample from. And it controls important properties of the functions non-parametrically, such as continuity, order differentiability, periodicity, scale, range, things of that nature, which are, important for a data analyst. So why are they useful? Well, they can be trained on noisy observations. And the first level of training is that if you have any parameters, which are referred to as hyperparameters in your mean function and kernel, you can actually write a likelihood function and adjust those parameters to conform well to the data. More importantly, however, you can also use them to make posterior predictions of values at points that you have not yet observed or where the function has not yet been acquired. So, and the key thing, which is often neglected, often we do this thing, this Kriging type of, we only keep the mean function, and it almost always goes very near the data, and we're very happy with that because it gives us a smoothing. But it's important to recognize the fact that these are probabilistic predictions. You don't just get a mean function, you get a covariance. So you also get an uncertainty in that interpolation. So how does this work? Just for the sake of visualization, I like to show this picture in which you have, if I have a multivariate normal, in this case, a bivariate normal, an X and Y, and I marginalize onto the X component, you get basically this normal distribution with the prior mean and the prior covariance. Now, if I make an observation of Y, I actually change the distribution over X. I shift the mean over in this case, and I actually reduce the variance because I've actually added information. So this is what happens in finite dimensional multivariate normals. A very analogous thing happens with Gaussian processes over the space of functions. Here, if the analog of observing a number of components from a multivariate normal is observing a number of function values in the space. And so here you see you have a prior, this is basically, I think I chose a Matern kernel here with this mean and this typical variance. And these are basically sample functions drawn from that distribution. What happens if you observe a couple of sample points from the function, with noise, is you get a new mean and a new covariance, and which allows you to make predictions elsewhere in the space. As an aside, I'd like to point out one very nice feature of Gaussian processes that one would wish deep learning models have. And so I draw your attention to this area to the side, which is outside the support of the training data. You see that what happens is inside the support of the training data, you get this characteristic snake, bumpy snake, where the variance is smallest near the data, and then it grows at some rate. And then as you move away from the support of the training data, the mean moves to some fixed value, and the variance moves to some fixed value. And if you've ever asked yourself, if you've seen this, and you ever asked yourself what this is, this mean is basically a kernel-weighted mean of all the data that it saw. And this variance is a kernel-weighted variance of all the data that it saw. So this amplitude is more or less the characteristic variance of the data. So what it's telling you, in effect, is I've told this, my model I've chosen a stationary model. So I basically told it that the statistics of the data are the same throughout the real line. And it says, fine, okay, boss. If you ask me to make a prediction out here, all I'm going to tell you is that it's going to be a Gaussian prediction with this mean, which is a mean of all the data I saw, and this variance, just the variance of all the data I saw. I'm not going to wiggle around crazily. I'm not going to hallucinate data that isn't there. I'm just going to tell you all I know. And this is very nice for a couple of reasons. One is this is a very reasonable prediction. Another is that if you see this mean and you see this variance, you know that you've moved beyond the support of the data, of your training data. And that's a fantastic, this is easy to see in one dimension, but it's very, very difficult to perceive in high dimensions that you've moved beyond. Oh, the third thing it's learned, of course, is the scale length on which this happens. So imagine that you have a cloud of data in a high dimensional space. It's learned some measure of how far it can move from that training data before it gives up and stops making detailed predictions of the data. Deep learning methods never do this, or you have to do a huge amount of work in order to make them do this. And so I think this is a nice example of a kind of property that we'd like to build into deep learning methods. Okay, so I think I spent a little bit too long on this slide, but I like emphasizing that point. So because Gaussian processes have the ability to make these probabilistic predictions, they've been very popular for data analysis and UQ applications such as image reconstruction, surrogate modeling, emulators for expensive simulators, black box functional optimization, optimal experimental design, which here in this community is called DOE. In my community, DOE is my employer. But there's this question that often comes up when, workers in this field present these uncertainties associated with the Gaussian process. Sometimes some smart ass will stand up and ask an embarrassing question, which is, what meaning am I supposed to ascribe to those confidence intervals from a Gaussian process? How are they to be interpreted? What is the calibration statement for them? What is their coverage? Okay. In other words, what is this blue band for, and what is it good for? Okay. And I used to just ignore those questions or be very cavalier about them because, how can something that gives you an uncertainty be useless? It's got to be good for something. Then I got religion when I had an experience in which I designed an algorithm with my collaborator, Mariam Ngom, called targeted adaptive design. And this is a Bayesian optimization. It's target optimization, really. The problem is that if I have some complicated experiment with some knobs, which here we'll call X, and some transfer function to some material that is made or some object that is made with some list of features, okay? So that's, I don't know this function f of x, but I want to make a thing f with some features within a certain tolerance, okay? And I want to do it efficiently, so I have to explore this function by experiments, expensive simulations, but I want to do it preferentially in the region that produces the thing that I want, okay? So here is an example. Here, this band is the tolerance box that I'm trying to hit. You can see that the real solution is going to be somewhere over here. Here I've added these points that have maybe, that have reduced the uncertainty, and it thinks that the most likely place is here, which is wrong. So it adds a few more points, and then it reduces the uncertainty here and it decides, oh no, this isn't right. And then it adds some more points here, and finally it converges. Of course, it's possible that you might have asked it for an impossible thing to make, in which case the tolerance box is below the actual response. And so you want this thing to actually squeeze out all the uncertainty from the function and eventually conclude, no, you can't have that, okay? Right, so the way it works is it replaces the unknown response with the vector valued Gaussian process surrogate model. It's vector valued because it's trying to predict many features. And it sends out a cloud of, it has 1 point, which are points that are already in the can, and 2 points that are points that we could acquire. And it tries to optimize over these 2 points and a target point. So it adds these 2 points and calculates basically the expected value of the surrogate at the target points. It hasn't acquired it yet, so it has to calculate the expected value. And it tries to find where the Gaussian process surrogate, where the target has an uncertainty that fits inside the tolerant box. At the end of each iteration, and this is the key thing, it actually acquires the function value at the optimal probe at target points, okay? Now, the picture that I showed you gave you a very happy story in which there was a convergence. But early on, we had this, all this beautiful mathematics that we believed and an algorithm that didn't converge, okay? So this was concerning. We actually made a test case where we knew where the solution was, and the algorithm would sort of approach the solution and then would stagger around like a drunk for a while and then zoom off. So we were like, what's going on? So this is the acquisition function. It's basically the expectation value over the unknown function values of the 2 points that we haven't acquired yet of the probability that the target is the one that you want, okay? And it would approach and then leave. So we investigated this. What we found is that it was making terrible probabilistic predictions of the function near the optimization solutions, okay? These acquired data, when we acquired them and we compared them to the distribution that they were supposed to sit in, they just were not plausible samples of that Gaussian process predictive distribution, okay? And the way we could tell this, and this turned into a key tool that we used to fix the problem, is that if you have the predictive distribution from a Gaussian process, this is the thing that sits in the exponentials, the quadratic form, and this thing, it should be distributed as chi-squared with a number of degrees of freedom equal to the dimension of this vector. And you can see that simply if you diagonalize this thing, it turns into a bunch of IID normals, so that those things are distributed as chi-squared. Well, this was the tell. We looked at this thing, and not only was it was nowhere near chi-squared. It was giving us enormous p-values. So we fixed the problem by monitoring this chi-squared, and each time it started to get too large, we basically add flexibility to the covariance. We basically add components to the covariance to make it more capable of adjusting to the data, and so that it could fit the data correctly. And then we got a convergent algorithm. So this is how these are p-values. And what we did is we set some threshold, and if it went down the threshold, we restarted it once just to make sure that it wasn't just too low by coincidence. But if it did it twice, then we updated the kernel model, and then it would be okay again. Then it would crash and bounce a couple times, and then go under the threshold, and we restarted. And so this was a case in which it converged to an existing solution. This is a case where there was no solution, and you can see the same pattern where it sort of bounces up and down a few times. But eventually you get flexible enough that you get good coverage over the data, okay? So this is the reason I got religion, is like if not making sure that your kernel fits the data can give you an algorithm that doesn't converge, then there's some relevance and importance to making sure that your kernel is sensible and describes the data. Moreover, this tool that we discovered, this is basically the p-values from these chi-square distributions. You see that they're not really very uniform. You don't really expect them to be because they're not really IID. But this tool, this Mahalanobis chi-squared, seemed to us like a very useful thing to use as a kernel validation tool. Okay, so what you need is either you need data that you acquire after making a prediction from a prediction acquisition cycle, or else you need holdout data in order to do this. Okay, so I started doing some numerical experiments to see how you can make this work and how you can refine this. Okay, so here's a one-dimensional model. This is basically drawn from a 1.5 new Matern covariance. This is basically this is a covariance that governs a space of functions that are only once differentiable. So they're quite rough, as you can see that it's sort of a bumpy function. And here are some samples with some noise added. So let's fit that with a really misspecified model. So this is a squared exponential, which is also known as the RBF function. It governs a space of function that are C infinity. They're smooth and they have a single fixed length. Okay. So the band is a 2 sigma credible region. And as I said, this kernel model is very misspecified, but the mean prediction actually looks okay. All right, it does basically what the method practically guarantees it's going to do. It goes through the points, okay? But so here are 80 yellow points that were not used in training, okay? And if you do this Mahalanobis chi-squared trick for the holdout data, you get 129 for 80 degrees of freedom, which is a terrible p-value. And so that means that if I'd actually tried to predict the values of these points before acquiring them, I would have made very, very bad predictions. Okay, my uncertainties here that I claim are my UQ bearing pieces of information about my Gaussian process interpolation would be worthless. Okay, because I misspecified the model. Okay, so is Mahalanobis as well as we can do? Well, the thing is, if you get a good chi-squared, that doesn't necessarily guarantee that you have a good model, right? Because what could happen is that you could have some components some residuals that are too big, some residuals that are too small. You don't want either of those to happen. You want them to be sort of governed by a normal distribution, but you get a situation where by accident you get a good chi-squared, right? Well, we can do better. If you take the predictive covariance and you diagonalize it, what you get is, you have we know that symmetric positive definite matrices can always be diagonalized by an orthogonal transformation. And if I make this vector of residuals in this way, these residuals are all, because the covariance that governs them is now diagonal, they're basically IID and they're normal with mean 0 and variance, and this should have been sigma squared k, sorry. Okay, so I can use this because now these things are independent. And so I can plot I can take their CDFs and plot them and see whether they're uniform 0, 1. And guess what? These are the 80 testing points. And I can fit a beta distribution to it. And here's the best fit beta model that I got. I didn't fit to the bin data. I fit to the unbin data using a inhomogeneous plus likelihood, which is just the product of all the beta densities. Okay, and you can see that the best fit model is telling me that there's really an excess of too small and too large residuals in this case, which was the thing that one has to worry about. you can make this a bit more quantitative. You can trade in that likelihood for a Bayesian posterior over the beta parameters. And here you can see what happens. This is the model, the beta model that corresponds to a uniform distribution, 0, 1. This is what actually happened. And you can see that, the values of A and B that correspond, this one, they basically correspond to a contour that I haven't shown here that contains almost all the probability. There's only 1.3 × 10⁻⁴ outside of it. So you can quantitatively say this was a crappy kernel for this data, okay? Now, let's try with a better model. I'll try to go quickly here. This is still misspecified. It's Matern with 2.5. So this is basically twice differentiable functions instead of once differentiable functions. But despite the misspecification, and I did this because we never know what the underlying model is. So it's unfair to use the correct model in this case. But models really only need to be good enough to give you adequate predictions. So this shows that it is possible to have a misspecified model that gives you an adequate prediction. So in this case, we get, a very respectable p-value of 30%, 31% in this case. And if I play the same game with the residual analysis, here's the posterior that I get. Despite the misspecification, it actually fits quite well. So those predictions of those 80 yellow points that I showed you earlier, the uncertainties that come from this model would have been trustworthy, okay? And this is how you know. Just quickly, if you go to 1D scalar functions are very easy to fit. I did something trivial here. I just picked a one-dimensional, I replaced one kernel with a different kernel, and I got a good model. Life is never this easy. As I showed you in the TAD model, in which the input is multidimensional, the output is multidimensional, it's a lot harder because now in multi-dimensions, you have to worry about correlations between dimensions. And often people use, factored covariances or isotropic covariances. And those, I think, in almost every case of practical interest are going to be awful choices. So, in the TAD example, what we had to do is play the kind of games with the convex combinations of kernels. And we managed to get to a point where we had at least adequate fits, okay? There are other games that you can play like that. If you ever look through the Rasmussen and Williams book in chapter 4 on kernelology, there's all kinds of tricks, including warping, multiplication of kernels and so on, where you can really go nuts on choosing kernel forms. But what I'm telling you is that you can use these same methodologies to validate your kernel. You have a lot of freedom of what kernel forms you choose, but you should not stop until you get a model that actually is satisfactory. Because if you do, you're not going to be able to you should not be able to persuade anyone that the uncertainties that you're predicting are worth what you're saying they are. Okay. So here's my summary. It's in fact quite possible to ascribe some quantitative meaning to a GP predictive credible region. But the key is that you have to test, and this is a great theme for this conference, is testing. You have to test with data held out from training, okay? And it's surprising how rarely this is done in the literature. I mean, sometimes people do leave one out testing. The fundamental paper from black box optimization, Jones and Schonlaw, made a big deal about how important it is to do leave one out testing. It's surprising how many people cite that paper and don't do that, okay? So they furnish probabilistic predictions, not just predictive means. And if those distributions are wrong, the UQ consequences cannot be trusted. And you can verify this. And you should verify this. Thank you.
We have a few minutes for questions. Do we have any questions?
Yeah.
So if I've understood you correctly, this will tell you if you have chosen a crappy kernel, as you put it, right?
Yeah.
And I'm not an expert in GPs. I don't know the state of the art or anything, but are there algorithms that could be used, using the convolution of kernels and stuff to find you a good kernel for your data?
There is a subject called kernel learning, which, I only have knowledge of at the cocktail party chit chat level. But people do attempt to optimize over larger families of kernels, but without making them too general. I mean, in the TAD case, we did something really simple because we wanted to have it, we wanted to be automated. At first Mariam was changing these kernels by hand, and then she got tired of doing that, and so she did something more clever than that. But all we were doing is basically adding components of basically the same structure of kernel. I think there's probably circumstances in which you can do more sophisticated things. In fact, I'm sure that there are, and I've only really scratched the surface of this subject. Really, all I've done is provided a methodology for doing this. Yeah.
As a metric.
Yeah, you can actually get a number. And I could imagine situations in which you start out and you have so little data that your kernel is naive. And then you do this and you make your kernel more flexible until it seems to adequately fit the data. But then as you acquire more and more data, that data starts to reveal structure in the function that wasn't evident at first, and now your model starts to suck again. Yeah. So you can get better and then get worse and then get better again. I think you just have to, the criterion, since you know that you're never, ever going to really recover the true underlying data generating model, your standard has to be good enough for the purpose that I'm going to put this to.
You like adaptive kernel building while you're doing your Bayesian optimization, so you get more information and change the kernel in the loop.
Well, in a sense, we did the simplest version of that in TAD.
I see. Okay. Cool. Thank
you. Yeah.
On the slide that where you showed the trying to optimize the value where the value fell well below all of the current predictions. So that was the one where it was impossible to find.
Yeah, I'll get it.
For that. For this one, why did it not, given that the value was outside of the uncertainty of the entire model prediction to begin with, why didn't it just reject it right away?
Well, you don't know at first that that's true.
Well, so is it coming?
This is just an illustration that I made up to show.
Okay, so at the beginning, you're saying you have nothing.
You know nothing. Maybe you have an initial design
with some data and having this and then trying to optimize on that.
That's right.
Nothing and then you say, okay.
What we did is we created a criterion so that we didn't necessarily have to search the space exhaustively. We just searched it enough so that we squeezed out as much as required to be able to say with good confidence that the solution didn't exist.
So you need some minimal design to begin with to probe this space, or else your uncertainties are gonna.
Well, we start out, with just. You can start with a design, and that's probably if you have one, of course, you should use it. But you can also just start with a few points and just let them wander around and populate the space.
Thank you.
Sure.
All right. Thank you.